This one's going to be an x to the fourth. Let's remember, say you, on part one of the test today, will be the graphing, right? Part one's going to be the graphing, just like the practice exam. Would be a bunch of graphs. And so you might see, for example, y equals x squared. So what's the basic look of y equals x squared? It's a U-shaped parabola, right? Does like that, right? So I hope you have the big 6 on your 3x5 card. You get to use a 3x5 card today on the exam, right? Parts 1 and 2. If you don't have that ready, you might want to cut out a piece of paper that's about 3 inches by 5 inches and write some good stuff on the front and the back in these next 30 minutes. But anyway, so I hope you have on there the big 6. And one of those being y equals x squared. And what do you think, and let me, by way of comparison, what about y equals x cubed? What does that one look like? It's another one of our big 6, right? X cubed? That's the snake one, right? Snakes on through, like that. Okay, so what do you think is going to happen, I bet you can tell, if we change it to x to the fourth? X to the fourth compared to x squared, you know what it's going to do? It's going to look almost the same. It's just going to pull it up a little faster, but it's going to basically look the same. It's just another U shape. It just goes up a little faster, but really it's basically a U shape. And what about if they give me x to the fifth? Guess what that's going to be like? Just like x to the third. But it's going to go up and down a little bit faster because it's got a bigger power. So I just want to point out, we're just going to extend now here in Chapter 4 what we learned already in Chapter 2 about graphs, and that is that odd powers, so anytime you have an odd powers, they're going to look like snakes, aren't they? They're going to do the snake thing. And over here we have the even powers, and the even powers are always going to do the U-shaped thing. Why? Why do the odd powers go down and up, and the even powers just go up? You know, right? Why? Why do even powers only go positive? Because it's an even power, right? If you do a negative, if you plug in a negative number to the second power or the fourth power, it's going to be positive. Right? It's like the absolute value. It makes everything positive. That's why the absolute value bounces up, huh? Because it makes everything positive. So whereas with the odd powers, when you put in negative, it remains negative. That's why they have a downside, don't they? That make sense? All right, so with that in mind then, let me put this one on a fresh screen since I scribbled all over that one. So they're asking me, they're saying, all right, what graph, which one of these graphs is x plus 3 to the fourth? So as soon as we see fourth, we're thinking, okay, it's basically a U-shape. You know, it's x squared. It's basically a U-shape. What is that plus 3 going to do? Yeah, it's a left 3, isn't it? Left 3. What if the 3 had been like that? What would it be if it was like that? Up 3. Yeah, let's get a little review for what you're about to take here in half an hour. Right? Up 3, right? Because if it's out here, it's a y effector, right? It's outside of x's little world. It does an up-down kind of thing. Positive being up, negative being down. Whereas if it's in the parentheses, if it's in x's little world, it's an x thing, right-left kind of effect. And remember, x always does the opposite, huh? Positive is actually left, and negative would be right. So you know all that. So this is a left, so this is basically a U-shape moved left 3. So take a U-shape, go 1, 2, 3 to the left. There it is. Which one of those does that? Looks like B, doesn't it? And we're done. That good? Easy enough? Hardly even new, right? About what we learned last time. Okay, so y equals 9/2 x to the fourth. So it's going to be a U-shape. What's that 9/2 going to do? Is it going to move the graph, or is it going to stretch the graph? It's going to stretch it. Why? Why does it stretch instead of like move it up 9/2? Because it's times and not added, right? Because it's 9/2 times, right? So that's going to, 9/2 is like what, 4.5? So it's bigger than 1, right? So it's going to go and stretch it vertically. Right? You got to make that sound when you do it. No. So it's going to stretch it vertically. It's going to be 4.5 times as tall. It's going to go up 4.5 times as fast. Whereas if we had this, if we had x to the fourth plus 9/2, that would move it up 9/2 or 4.5. The U shape would go up here, right? The middle, the origin would be moved up, right? Whereas this one, whoops, there's my pencil here. This one is that, whoop, that's the wrong thing. Come on. Oh, there we go. So this one is going to just go up faster, but the origin's going to still stay planted where it was, huh? Y'all with me? See the difference? It's still planted where it was. It's just going to go up faster. Whereas if they added the 9/2, so adding, subtracting numbers is what moves graphs. Multiplying numbers stretches or compresses. So that's a stretch. Okay. So, okay, which one of those U-shapes? So it's not this one, huh? Because those two have been moved. See how the origin has been moved? It's not those. So it's either A or D. Which one is it? You know what we could do? Make a table, huh? Just plug in a couple values. So let's do that. Let me just get this out of the way. So let's plug in a couple values. Let's make a little XY table and just say, all right, if I take this right here, y equals 9/2 x to the fourth. What if I plug in, I could do 0, but that's just going to be 0. Nothing amazing there. 0. But if I do like 1, how about that? I just plug in easy numbers. Just x is 0, x is 1. What's y going to equal? 9/2 times 1 to the fourth? Just 9/2, huh? So over 1 up 9/2. So there it is. Over 1 up 9/2. It's C. Good? Questions on that? Easy stuff for you, I think. So how about y equals x minus 1 to the fifth plus 8, like that. So how do we graph that thing? So first, so what's this plus 8 going to do? Up 8, huh? Up 8. What's this minus 1 going to do?
Right 1.
Yeah, it's opposite, huh? Negative and positive, so it's right 1. And it's basically the fifth power, it's odd power, so it's the snake, huh? Which they're all snakes, so it makes sense. So you're going to take the origin, take the point, which is the center, which is normally at the origin, and go right 1 up 8. So go right 1 and 2, 3, 4, 5, 6, 7, 8, way up here. So there's the new origin. Now, don't be confused by the tail. I think we talked about that last time, didn't we? It'll still have a tail that comes down eventually and hits the x-axis and goes up forever as well. But the center has been moved, hasn't it? From the origin, right 1 up 8. So which one of these graphs has the center having been moved to the right and way up?
D.
Yeah, it looks like D, huh? Because here's the center about right there, you can tell. Right and up. Whereas this one's down, no way, A's down. B is up, but it's left. See the center on, and B is over here to the left. So it's D. Good? Easy enough? Okay, so we have y equals 2 minus x minus 1 to the fifth. Okay.
Thanks.
So fifth power, snake graph. Let me give you a second, rather than me just fly through it. Go ahead and see if you can see the pictures there. Do whatever it takes. Oh yeah, this is a hard one. How you doing? Can you tell? A little tricky. This is a little tricky. Anybody feel confident? Yeah.
B.
B. Why B?
Well, because if you plug in 1, then you get 1, 2.
Good. You're plugging in points. It's a good way. Well, wait a minute. He's got 1, 2 also.
But it's not negative.
It's not negative?
It's 2 minus 0. It becomes 1, 2 after you plug in 1.
So you have the negative 1.
Right, I'm with you, but are you with me? They both have 1, 2.
Yeah, but that's a negative 1 on C.
The negative.
Negative 1.
Oh, is that a negative?
Yeah. Yes. It's on the left side.
Oh, of course. Yeah, I'm not looking close. You're right. You're right. Good. Good. Excellent. Of course. Now, negative was little, but of course it has to be negatives on the left side. Good job. Yeah, it is B. It is B. Yeah, so let me help with that if you're at all confused. So first off, let's go through the various pieces. This 2, you know, that's out front, it might throw you off. I don't know, maybe it doesn't. It might be easier to do it that way. That's the same thing, huh? Because that's a positive 2, right? When he was here, he really had a plus sign in front of him, didn't he? Remember, signs in front of numbers or letters or whatever, that's their baby, right? Take that with them wherever they go, right? So when you move that 2, it might, so you don't have to do that, but it might be easier to, that's how we're used to seeing it. So this is up 2. This is, minus 1 is right 1. And what is that minus sign going to do? Flip it. Now there's 2 ways to flip it, sideways or vertically. Vertically. Right? It's an up-down flip because that's a Y. Whereas if it was in there on the X like that, that would be sideways. That'd be a sideways flip, right? You're good with all that? Whenever something's right in X's world, right on X, that's a sideways flip, a negative sign. But if it's out, removed from X's little world, it's a vertical thing. It's a vertical flip, right? Okay. So that means if you take the snake graph and you flip it upside down, then it's going to go like this. Isn't it? So generally we're thinking about an upside down snake graph that has been moved right 1 up 2. So take the snake graph from the center, the origin, and move it right 1 up 2. So right there, it's going to go right there. That's what this one has done, right 1 up 2. We good? Questions on that one? Now, if you're it's good. I like the way it was commented that points were plugged in. That's smart. That's a really good idea because the way I'm doing it right now, where I just go, hey, right 1 up 2, that's it, it's good. Actually, I'm being a little too casual. You know, it's good to plug in points. That's a better way to go because remember how you can fool yourself when there's both a flip and a movement on the same axis. We talked about that a little bit, didn't we? That's the trickiest thing about these things. Because if you move, say, because this one said up 2, right? Whoops, I'm erasing it. This one said up 2. So if you move, you might think, well, it's up 2. How could that be confusing? No. Remember, if the up 2 was moved first and then the flip, it would actually end up down 2. You remember what I'm talking about? When there's, so let me say it again. When there's both a flip and a movement on the same axis. So notice if it moves up and down and flips up and down, or if it moves sideways and flips sideways. So in this one, it is flipping vertically and moving vertically. The order matters. Remember me talking about that? If you flip first, which turns out this one does, then it's not a big deal. You flip first, then you move. Up is up. But if you move up first, then flip. Because remember, the flip, here's what confuses people. People think maybe they think it just flips standing in place. It doesn't. It's world flips. Like you grab it by the axis. Remember, the way we're flipping is rotating axes, right? We're grabbing that like a rotisserie on a barbecue grill. We're turning it. And so that means this up would flip down then. Even though it's up in the equation, it would end up graphically down if the flip was after the movement. Well, how do you know if it's after or before? I could give you all the rules, but it's confusing. It's much better to plug in points. So what I would do, rather than look at that and with confidence say, hey, it's up 2, it's up 2, it's up 2, I'd look over and go, maybe not. Maybe if the flip's afterward, maybe not. I'm going to be sure. So just like it was said, let's plug in points. That's a good way to go. Then you're sure if you plug in points. So I would just plug in whatever's 0, plug in 1. And then you go, okay, y is negative. X minus 1 to the 5th plus 2. Plug in a 1 here. Got too many equal signs there. That's all 0 minus 0 plus 2. Okay, sure enough, it is over 1 up 2. It really is right there. Now I'm confident. That's the way to be sure. Do that on today's test, right? Be sure about those because, again, the order matters. Up could end up down if the flip is afterwards. So, all right, let's keep moving. So that was all kind of stuff that's going to really be on today's test with third powers and second powers instead of fourth and fifth. So now here's something totally new. So form a polynomial, and there I've actually done it for you already, whose real zeros and degree are given. Okay, what does that mean, zeros? What are the zeros of a polynomial? It says the zeros are -1, 0, 9. Do you guys know those are x-intercept points? Zeros are x-intercept points. It's points where the graph is at a height of 0. So that means at back 1, at 0, and at way over here at 9, the graph must hit the axis. Those are zeros. And so the graph must do something like this, like boom, boom, boom. I don't know exactly, but generally, probably something like that. Because those are zeros. Now, they didn't ask me for the picture. They asked me for the equation, which I did here. So basically, you see how it works. You just take the opposite of each of these numbers, don't you? So I'm going to do, the order doesn't matter. I'll do the opposite of negative 1 first. So that'd be x plus 1. And then this would be just x minus 0, if you want. So, and then x minus 9. That's the function. Why? Why is that the case? Well, because, this is what f of x equals, because we're making something for which negative 1, 0, and 9 are zeros. Meaning, if you plugged in negative 1 there, it would make that piece 0, wouldn't it? We good? Everybody see what I'm saying there? If you plugged in negative 1 plus 1, that piece would be 0. And if one piece is 0, since they're all times, the whole thing is 0. Right? And if you plugged in 0 here, of course, that would be 0. If you plugged in 9 there, that part would be 0. So there we go. There's the function. With a coefficient of 1. Really, it could have any number in the front. They're just saying assume it's 1 in the front. All right, we good with that? All right, so number 6. 0. So yeah, let me write this out maybe in a way that's easier to see. So 1, 0 is negative 3 with multiplicity. We'll talk about that. 1. And then another 0 is negative 1 with multiplicity 2. So we got a 0, which is negative 3, multiplicity 1, and negative 1, multiplicity 2. So first off, and they want the equation. So the equation, the function. What am I going to do with minus 3 first off? X plus 3, right? Good so far? Multiplicity, do you know what that means? That means the power on the parentheses. So first power, or just regular, in other words. Next one, what do I do for negative 1 with the parentheses? It's always the opposite sign, huh? Because that's what will make negative 1 make that 0. Good, right? Just do the opposite side. And what's the power? Second power. That's what the multiplicity means. So multiplicity means the power on that parenthesis. So there it is. There's the function. It said degree 3. That is 30. If you FOILed that out, it'd be x third in the front, wouldn't it? You know, if you FOILed the whole thing out, it'd be third power. So we're not going to bother to do that. It'll take this answer like this. I wouldn't multiply it out. Just type that in. Math Excel likes that. It's happy with that. Hey, by the way, if I was to graph it, we're going to graph them well, next week. We'll graph them. So let's go ahead and take a look at that right now. If I was to graph it, that means at minus 3 and at minus 1, there would be zeros, right? Right, that's what it means to be zeros. And so maybe the graph would do something like this, you know, something like that. Well, actually, no. Not quite. Did you know what the multiplicity means? What does it mean that at this 0, this is the negative 1, 0. Negative 1 would make that piece 0. The multiplicity is even. Even multiplicity. Do you know what that means the graph will do at that point? Does anybody already know that?
We go like a half parabola.
Yeah, it'll bounce. Exactly. Instead of passing through, it'll bounce there. So it won't actually pass through that point. Let me get rid of this. It'll bounce back up like that. So at even powers bounce. Even powers bounce. Why do even powers bounce? Well, you know, because even powers can't be negative, huh? Right? Just like we talked about. It's squared. So no matter what you plug into this guy, it's going to be positive, isn't it? It's not going to go negative. It's going to bounce. And then odd powers? Odd powers are not going to bounce, just like x cubed and x to the 5th, huh? It's going to pass through the point. So this one will pass through. So negative 1 bounces, negative 3 passes through. That's generally what the graph's going to look like, which they're not asking me on this problem, but they will soon. Okay, so they got this big function. Can you all see that? So let me make it a little bigger here. So f of x equals negative 8 x squared plus 16 x minus 4 to the third. Okay, so first question is list each real zero and its multiplicity. So what are the zeros? So now we're going the other way, huh? The last couple of problems, they gave us the zeros and they wanted us to provide the function. Now they're giving us the function, they want us to give them back the zeros. So what do y'all think? What could you plug? So when we say a zero, we're saying what x values plugged in, you know, there or there, make the whole thing equal 0. That's what it means to be a zero. You plug into the function, the whole thing becomes 0. Yes, that's an obvious one, huh? So 4. If you put in 4, that piece is 0, so there's 1. Good. Is there another one? 4 will make that piece 0, and since they're timesed, the whole thing 0. Good so far. What about that? What about this x squared plus 16 thing? Can't make it 0?
Don't touch.
Good. Exactly. There's no way to make that 0. Does everybody see that? There's nothing you could plug in there and then square it, because that'll make a positive, huh? And then add 4? It's going to be positive, isn't it? There's no way that's ever going to be 0. That's good. I like the way you guys are thinking right now. That's the way you want to think. What a lot of people do, a mistake that this one really gets a lot of people, is they'll go x plus 4, x plus 4. They think you can factor this like that, and that's not true. I hope you know that. Really important. Let me, you know me, there's no secrets. That's all. Something just like that is on exam number 2. I just made exam number 2 this last weekend. That's on there, and I'm not trying to torture you. I'm trying to get you ready for calculus. That comes up all the time whenever I teach calculus. Is people that struggle with that particular factoring and just keeps nailing them. So I want to help you to be ready this semester for that. That's not true. Do you know that? X squared plus 16 is not x plus 4, x plus 4. Let's check it. Let's see. What do I mean it's not true? Well, I mean if you multiplied it out, it will not be x squared plus 16. So x squared plus 4x plus 4x. See the problem? Going to get 8x in the middle, huh? See that? You know, you cannot factor when you have what's called a sum of squares. Remember, the other one's called a difference. So minus in the middle, totally. And that's what confuses people, right? If you have the minus in the middle, yeah, remember how that works? That totally factors. And that's 1 plus 1 minus, exactly. But if there's plus in the middle, you can't do it at all. That makes all the difference in the world. You cannot factor a sum of squares. It just doesn't work. It gives you a middle term. You can't have that. You got to get that to go away. So make sure you know that. That's really, really important. It comes up a lot. All right. So because it can't factor, you can't do that. Then I like the way you guys were thinking about it. You just look at that thing and you just say, look, there's nothing. There's nothing you can put in there. It's going to make that 0. So this is the only 0, huh? Just x equals 4. This x squared plus 16 gives us nothing. No help at all. Okay, let's keep moving. Question B. How are we doing on time? We're doing good. Okay, question B. Determine whether the graph crosses or touches the x-axis at each x-intercept. So that's the whole bounce, pass through thing that I was telling you about. So let me write that down here. This is part A. So part B. So they're saying at each x-intercept. Well, what are my x-intercepts? Just this one. Zeros are x-intercepts. Those are synonyms. Those are the same thing. Zeros and x-intercepts. So zeros are x-intercepts. There is no difference. 2 words for the same thing, synonyms. So we're talking about x equals 4. That was our only 0, our only x-intercept. So at that one, at x equals 4, is the graph going to bounce there or is it going to pass through there? What's it going to do? If I was to make this graph, let me get this out of the way and make a little artificial graph. So what we've discovered so far about this graph, if you do the x-axis, y-axis, at x equals 4, 1, 2, 3, 4, right here, this is the only place our graph hits the x-axis, huh? It's the only place. Now, what's it going to do there? Is it going to touch it there or bounce it there? How do you know? You look at the power on that term. Third power. And what does that mean? Odd power? pass through. It's not going to bounce. Remember, even powers make you bounce because you can't be negative, right? So it's going to pass through. So it will pass through. So that means that, that means the graph's either going to be up here and pass down through there, or maybe the other way, up here and pass down through there. We don't know. We'll know in a minute. Let's keep going. C, determine the max number of turning points on the graph. Yeah, max number of turning points on the graph. So right down there, okay. Max number of turning points equals degree minus 1. Did you know that? Have you seen that before? So whatever the degree of the polynomial, there's at most, there could be less, but there is at most, there's a maximum of that degree minus 1. Turning points. Let me show that. Let me go to a fresh screen. That's just a mess. And show you some examples of that. So it makes more sense. So again, number turning points, or max, because there could be less. The maximum the most you're going to have, the maximum number of turning points is degree minus 1. What does degree mean? Power. Power of the whole f of x. So if I was to take this f of x, I'm going to come on down here. If I was to take this f of x function, which is what? Minus 8 x squared plus 16 x minus 4 to the third. If I was to multiply that entire thing out, I don't want to do that. That'd be a big pain. I'm not gonna. But you know what I could do easily? Is find the front term, the most powerful term, if I was to FOIL that entire thing out. The front term is easy to find. What do you mean? How do you find the front term? And when I say front, because it might not be front, it's highest degree term. That's what I want to say. Highest degree term, which is, usually we put that in the front, but technically it doesn't have to be. So highest degree term, usually put in the front. What's it going to be? Well, what you do is you just imagine if you did FOIL it out, but you don't really, but you just imagine, hey, if I did FOIL it out, minus 8 would multiply this and this, but I just care about the most powerful interactions, because I'm just going for the most highest degree. So I would have minus 8x squared would be the most powerful thing coming out of these guys' interaction, right? And then that would interact with this. Now this is x minus 4 3 times, okay? So what's the most powerful thing coming out of this guy? Well, when the x gets together with the x, gets together with the x cubed. So most powerful term minus 8x to the 5th. Everybody see that? The front, most powerful term, if you were to FOIL that all the way out, is going to be minus 8x to the 5th. How do I do that? You just grab the front thing times the most powerful, and this is basically going to be x cubed when you FOILed it all the way out. It's going to be the front term. So minus 8x squared times x cubed, minus 8x to the 5th. That's going to be the most powerful term. The rest of the stuff is smaller. This is going to be, there's going to be an x to the 4th term, x to the 3rd. Smaller stuff. Smaller stuff. Okay, so what does that mean now about max turning points? Max number of, so what is the most number of turning points that graph could have? This is his degree. Degree is your power, your biggest power. The degree is 5, so 5 minus 1, 4. So that graph has at most 4 turning points. Now, I haven't even drawn that. What does that mean? That just means literally turning. So, you know, from going down to going up, or vice versa. So now, when I drew this graph, I know it goes through 4. I've already decided that. It might go up and then come down and then go up and then come down. This would be a turning point, TP, turning point. And a turning point and a turning point. And maybe it goes, well, it's not, it can't. But maybe that goes down. Maybe it goes up one more time. I don't know. So these would all be, what's that, 4 turning points? These are all turning points. See those? It's going to have, at most, it might have less, but it's going to have at most 4 turning points in the graph, where it goes from going up to going down. That's a turning point in a graph. At most 4. It's always the degree minus 1 is the most. Does that make sense? That fits what you already know about x squared. Well, x squared, 2 power, how many turning points? Well, it's got 1. It goes from down to up. It's got 1 TP, doesn't it? 1 turning point. Now, you might think about x cubed and go, yeah, but x cubed, what about x cubed? X cubed, how many turning points does x cubed have? None. It never goes from up to down. So remember, it's max. It doesn't necessarily have that many turning points, but it won't have more than that. See what we're saying? That's the most it could have. It might have less, and some very often do. Well, we need to take our test, don't we? So let's do that. Let me stop.